Hi, everyone. Welcome. It gives me great pleasure to introduce Dr. Matthew Trussoni, who is going to be talking about integrating glass fiber reinforced polymers into sustainable building development. Dr. Trussoni is currently assistant professor in practice at the University of Miami. His professional registrations include PE, registered architect, certified general contractor in the state of Florida. As a practitioner, he owns and operates Trussoni Architecture Group and True Line Construction, LLC in Miami. He has been published in ACI Materials Journal, ASC Journal of Architectural Engineering, among other refereed journals. So thank you very much, Dr. Trussoni, for agreeing to do this, and we look forward to your talk.
Great, thank you for the wonderful introduction. It's really an honor to be here today and speak with all you students in the CAE department. I've been following these lectures, the ones that are relevant to me for the last couple of years, and the people and the quality of speakers that we have been bringing in is really impressive, and it's an honor to be included in the group. So thank you, and I hope what you guys find interesting what I have to talk about today, which is this residential building that you kind of see in the background here on my title slide. The product of many design meetings and many design different iterations that I'm going to take you through very briefly today. And then we're going to get into in depth a little bit on using the GFRP and actually also CFRP reinforced concrete in the design of the structure itself. So I wanted to start out with this slide. I knew that this talk was for a bunch of PhD and master students. And there are PhD and master students that are involved on this project. And as you guys can see, that kind of center circle is, probably the blue would be, a bachelor's degree. The green is going to be where a master's level student would be. And then you see the area of research. And, as scientists, which many of you are and aspiring to be, really what you're trying to do is you're trying to expand that knowledge boundary. And that expansion of that knowledge boundary is your PhD thesis and the papers that you're going to publish out of it. And so there is a lot of things that go into the design of a project. A project really needs to be well-rounded. It takes into account all areas of knowledge. If you look at the built environment in general, buildings and infrastructure, it incorporates, history and culture and all kinds of things that we're not going to talk about today. But when you're going through the process of designing those, you really need to incorporate those and think about those. And so the introduction of our kind of design team that we had for this project, I'm going to say is kind of the well-rounded bunch that is looking at all of these things. The client was Capello Manzano Partners. That is led by a gentleman, Dr. Ted Kaplow, who has got a PhD in mechanical engineering. By myself, they brought us into the project, the Trussoni Architecture Group, doing the architectural design jointly with Capello Manzano Partners and doing the structural engineering. And Energy Sciences, who's led by, you guys know this gentleman, Dr. Ezbrandaroglu, who's also part of the department. And, I'm going to talk about and list some of the incorporated technologies that we've been using, that kind of circle this whole thing. As we get in and talk a little bit more in detail about the structure of the project, we had a master's student, Jan Lin, who graduated last year. He's now up in New York working on getting his PE. But, he was very integral in doing a lot of the work, part of the structural analysis part. And I'll kind of point out where he did that within the presentation. Zahid Hussein, who is a PhD student of Dr. Nani's, put him over on the PhD. We actually have a paper coming out that he's leading the effort on the slabs, and I'll also point out the areas where he was involved in the project and with that paper. And then we kind of have the big topic of the presentation, which is the 440 code and the TMS 402-602 code. And I kind of put this big rupture in the knowledge boundary of what's happening with, introducing the FRPs into the building industry. I would say infrastructure and buildings, to be technical. I think it kind of started in seawalls and bridges, and now it's really going over with, ACI 440 and TMS 402-602 into the realm of buildings. So very exciting stuff, and all kinds of new knowledge that's being brought out and being implemented in in the built environment, from the University of Miami and other institutions. So I also organized the presentation kind of into these areas, right? The blue is going to be kind of our overview of all the things that go into the building that aren't necessarily structure specific. And then we're going to talk a little bit about like the design of the structure and the analysis of the structure. And then we'll go into more depth on the GFRP materials and, each one of the kind of members that get designed within part of that overall structural system. So we'll start out with the location. You can see here, the location is in North Miami. There's the address. It's a vacant lot. It's very close to the bay and very close to what we call the Little River area in Miami. It is very prone to sea level rise in high tidal times. The streets are often flooded. The lot gets flooded. It's at about 2 to 3 feet NGVD, what we call, which is basically 2 or 3 feet above sea level. So it gets a lot of that. And, there's this website by Miami-Dade County Office of Resilience that kind of outlines these sea level risks. And, if you guys are such interested, you can go. Some of you are probably familiar with it. But you can see the buildings that are highlighted in red are ones that are susceptible to sea level rise at different heights. And over here, they got little clickers where you can, change kind of the level of rise of sea level. So if we look at like a 3 foot, and even if we went down to 2 foot, you would see that, this area of Miami is very susceptible to the effects of sea level rise. And you can see here, here's our actual building site right here. Right now it's a vacant lot, and we'll be doing the infill project on that site. So if I close out of here, zooming in on the site a little bit, there it is. Basically it's about a 7,000 square foot lot, a little bit bigger than that. And so, to build a whatever 5-bedroom house on it, we're pushing up against the sides and all the setbacks, which you can see kind of typical happening with any new development of housing here in Miami. So when the client, Capello Manzano, brought me into the project, they had very specific program and design specifications that they wanted to meet with this. Even coming out with a list and providing it to us, and basically all the requirements for the overall project and what we have to meet. And I have them listed here. This is the kind of the spreadsheet, but I just want to point out a few. On the energy side and the certification side, LEED Platinum, net zero energy, electrical vehicle stuff. A big part, Dr. Capello being a mechanical engineer, he focused on indoor air quality a lot. And so he wanted, no drywall, which is very unusual for a Miami type construction because of the air quality issues. And so, there's some very unique aspects of how the mechanical system is organized, what we have in the mechanical system and how the structure interacts with that. We had created a core in the building in order to service those types of things. And of course, you can see the sea level rise stuff that we talked about already there. On the structural system side, there's at the beginning really no mention of incorporating any FRP into the project, but they were looking at an all concrete structure, knowing the resilience characteristics of all concrete, and they wanted to have it exposed. And so part of the reason probably why, I got involved is because they knew that I do all concrete structures, done several of them in the Miami area, over the last, few years. And so then also the mechanical equipment, very specific kind of requirements of what they wanted for the mechanical equipment. So we have a short list. There's other things I'm sure that I probably missed. The stuff that we're really going to be talking about today is at the top. And then we have also some other mechanical, electrical and plumbing innovations that we incorporated into the project, as part of meeting all the sustainability goals. And, I just like to say that the GFRP really fits into that whole sustainable picture really well. And I use sustainable because I think people have to distinguish a little bit between resilient structures and sustainable structures. What we found and what we kind of already always knew was that, resilient concrete structures are resilient structures. They have the strength, the durability to stand up to hurricane force winds, and when hurricanes come, and you know, at the end, we just had another devastating hurricane. We saw the pictures of the coastal areas devastated. This is a picture from Mexico Beach, Hurricane Michael, 2018. You can see everything around the all concrete structure basically devastated, and the concrete structure, metal roof, kind of sitting there. I don't want to say unscathed, but you know, resilient, right? Ready to bounce back. So that's, you know, the kind of the definition of resilient is you know, it comes back really fast. It's ready to be used right after an incident. And sustainable is long term, right? How are these things going to last and fare for the long term? And I think what we found out about corrosive reinforcements, steel reinforcements, is that they might not be as good on the sustainability side as on the resilient side. And so by incorporating non-corrosive reinforcement into concrete design, you're really addressing both of those things, the resilience to being able to bounce back right away, and the long-term implications of is that structure are going to be able to be withstand and be with us for 80, 90, 100 years time period, where we're finding, you know, the corrosive reinforcements are causing failures at, you know, 40, 50 years, even less sometimes. So we started out when I was brought into the project with something that looks like this. This is, you know, what we call the massing of the building. You can see, you know, basically it's pretty plain, right? Just the exterior envelope, you know, maybe the entrance exit. We knew that it was going to be elevated due to the elevation of the site. We knew that the site flooded because of the location and the elevation. And so, you know, automatically we have the structure raised up off the ground, elevated on pilotis or on columns, you know, very similar to stuff that they do in the Florida Keys, where you're, you know, right next to the water. In the rear of the project, we had an elevated pool deck, you know, that you would kind of come out of the back and, you know, walk down and have a pool of some sort in the back. And, you know, at this stage, it was pushed up against the property lines. It didn't end up getting pushed up against the property lines at all. And so as we got involved, we started to recommend some things on the structural design side, which was the front of the building becoming a diagrid type structure, right? We thought that this not only is a more stable structure for lateral forces within the project, but it also kind of expressed that resilience as part of the building structure itself. And in the rear, we had more of a conventional type framing system, where we would have girder slabs on beams, and actually we were thinking precast joists at first. They would be supported, you know, by girders, and then columns, straight columns coming down to the ground. You can see, I'm just going to point out a couple of things, the kind of idea of this core in the center of the building that houses all the mechanical systems, circulation, elevator, stair kind of thing. And then in the front, having an area where it's actually bedrooms. And then in the back, kind of the more public areas of the house, master on the second floor, and public areas on the ground floor that would lead out to the pool deck. And then in design development, you know, followed through on the same philosophy, refined, you know, the openings, refined the size of the diagrid, the size of the members, getting the actual dimensions and things on there. And so we ended up with a building structure that looked like this. This is from the building information model that we developed, you know, as we developed the project. And so, you know, you can kind of see here the different components that go into it that we're going to discuss and look at in a little bit more depth. You see that core of the building, some of the openings for some of the MEP equipment, the elevator. I think maybe we can see that a little bit better on the other view. So that core that runs through the center of the building. Slabs, we have upturned beams. You can see here, because this is going to be a habitable roof deck. And so we need to create a little area where we have a sunken structure so we can put the insulation on top. You can see, if we go to the view that contains also the aerated concrete block, walls, and the CMU walls. If we start kind of from the back of the project, we created that elevated pool deck with retaining walls, right? These retaining walls are going to be CMU walls, 8-inch or concrete walls, partially concrete, partially CMU, depending on their location. We'll go into that a little bit more when we look at the structure in detail, that support that roof deck, but retaining walls with a retaining foundation. We also have some retaining walls around the front of the site where we elevate the parking. And then we have infill walls for the rest of the building, but we can still see that core area that leads up to the roof deck that's on top. And then the insulation would be set within those areas, the roof insulation set within those areas. So you can kind of see the outlines of the, and so, you know, the final design ended up looking like this. A little interesting subject matter in Miami and in high velocity wind zones. You know, a lot of places in the country, they look at just the structural frame as part of the structure. In the high velocity wind zones, we look at all of the enclosure as part of the structure. And so, you know, the glazing, the windows, the walls that enclose the space, if those are lost during a hurricane, right, we lose the integrity of the interior structure. And that, you know, that once you lose that, right, then you kind of lose the whole structure. So in the structural design, we both have to be cognizant of that enclosure and the overall main force resisting system, as we call it, right? And so the diagrid in front helps with those lateral forces, the wind forces, where those get translated into axial forces, you know, very similar to how a truss works, except for within the whole system of the structural system of the building. Underneath, the cars would come and park under here, and then you can see kind of the main entrance into the house and a secondary entrance that's underneath. The area underneath the building is reserved for flooding, right? When it floods, that's kind of the area where the water can go and sit and then leach back down into the ground. So at the 50% construction document phase, as we went through this, we had designed this structure both out of steel reinforcement and out of GFRP reinforcement using the 440 code. And it was a very interesting time in the pricing of building construction. And I think I bring up the pricing, not because it has to do with the research, but it really has to do with more the implementation. And you see this kind of tidal change in use of materials or use of technologies when this economy of scale or the economics really switch. And what we saw, because we took the engineering for both structures and we got it bid out by structural contractors or shell contractors, to our surprise, due to inflation and other issues, the GFRP structure came in cheaper, not by a lot, by about $20,000, but came in cheaper than the steel structure. The steel reinforced structure came in, and we were not really expecting that at first. But after we went through the pricing process and found that out, we found out that, you know, now this turns out that it's going to be a more sustainable option and also a more economic option for certain building structures. Of course, not for all. We're talking about this specific project. But I think it's an inclination of what we're going to see happen, you know, in the future, as far as what happens with the implementation of the technology. All these things are kind of coming together at the same time. You know, the code being approved. I know it's approved by ACI. I think we're still waiting on the International Building Code on a vote from them, but I think that's coming shortly. And after that happens, then, you know, I think we'll see this get implemented into, you know, all of the other Florida Building Code and all the other codes that come kind of down the line from there. But as it stands right now, we can reference it in our construction documents, and the building departments can go forward and review the building structures with this type of reinforcement. You know, that combined with the economic motivation, the tools, right, and the motivation, I think we're really going to see, you know, the implementation of this material as another option within the structural engineer's toolbox to be able to deliver sustainable and resilient structures to the industry. So after the structural design was complete, we embarked on doing the structural analysis and engineering the members. Jan Lin really did a lot of this work. He built this analytical model, got a lot of the output out of it. analyze things a lot of different ways using it. And of course, when you do analytical modeling, you input all the geometry, input all the loads, input all the load cases, analyze those load cases against each other in order to see, what the worst case scenarios are as far as loading are concerned for each one of the members. And you'll see that at the end, I'm going to bring up the kind of the structural calculations so we can take a little bit look in more depth at that. And we'll see the output from this, but I just wanted to show that, at this stage, we were doing this, Jan did a lot of this under our guidance. Of course, we met, weekly to go over what he was working on and double check the members and remember the output and make sure everything's count. We also did a conventional analysis. Very often when you're designing structures, you're going to do multiple types of analysis. You're going to check all those analysis against each other to make sure that, what you're seeing out of one is copacetic with what we're seeing out of another one. Just so we don't have any major disconnects of what the loading is going to be on each one of the members or on the whole frame or on the whole structure in itself. And so, we did kind of the conventional analysis and the design of the FRP using MathCAD spreadsheets. And then we compared those with the output of the analytical model, and whatever one we felt was more accurate. I don't want to say the higher load case, but whatever one we felt was more accurate, we would go with and then use to design the members. So that really brings us to the ACI 440 and the Masonry Society 402, 602 codes. So I think everybody, I'm sure, is probably familiar with the American Concrete Institute, so I don't really have to go into that. The Masonry Society is a little bit less known. They govern all the design of any masonry, from block masonry to aerated autoclaved concrete block, which are the two types of masonry that we have in this project. But they also, glass block and, anything masonry, stone masonry, brick masonry, if you're looking to design those, that's kind of the code that governs that area. And in the ACI, the 440 was obviously the big revelation in the GFRP, getting that implemented into using in buildings. And in the TMS, it's Appendix D is where we see the use of the glass fiber reinforced polymer and how we integrate that into the engineering for the walls, for the masonry walls. There are some aspects that aren't covered in these codes. Here's just a short list that don't have implications within the ACI 440 or the TMS 402, 602, and need to be looked at a little bit deeper. Some of the main ones like that we had to do, I guess you would say, priority calculations on were the diaphragms. It's a flat plate, rigid diaphragm for the floor plates and the roof plate, but sizing the members to take the chord forces and those types of things. We did that proprietary calculations on for those. I think that's really the only one that we really needed to implement. One that I will point out, two that I will point out towards the end that have a limiting factor is the seismic. What seismic region you're in. We're in a very low seismic region here in Miami in category A. And so we can implement that. You can use this code in other seismic regions, but it's not allowed yet to be part of that seismic resisting system, the lateral force resisting system for seismic. And there are a lot of fire provisions about the cover of it and all that are based on the temperature of the bar. The temperatures of the bars when you implement that, and being a residential structure, our requirements for fire protection are much lower than what they are for a commercial type structure. So I know there's other engineers around the world working on buildings with FRP and commercial applications, and they're running into some limitations that the code and researchers are now working through in order to satisfy those concerns about the fire situation of FRP. But because we're a residential use, really we kind of, I don't want to say circumvent, but those aren't as much of a concern for our project. So you're all probably pretty concerned with the different, or pretty familiar with the different types of FRP bars. the different types of services that go into it. You know, the code like lays out all of these. The code lays out the fact that we need to abide by ASTM D7957 for the minimum standards. And those standards are laid out in all of these other ASTM standards. You can see mass content, transition temperature, degree of cure, ultimate tensile strength, you know, modulus of elasticity, to name a few. The most manufacturers, and I'll show you guys the manufacturer that we're using, that we specified in our calculations when we get to the calculations. But you know, all of them abide by this. They publish their own material properties as part of what they provide. And you know, usually when you're doing the design of that, you take those specific material properties and you incorporate those in your calculations as you move through. So looking at the different members, we laid out steps, part of the design process. We wanted to standardize this design process for all engineers that can take and implement 440 and 402 into the design of building structures. So for those of you that have experience with building codes, when you go into a building code, they never give you a step-by-step process in order to design a member. It's, you know, the flexural requirements are in one part of the code, the minimum sizing requirements are in another part of the code, the shear reinforcement requirements are in one part of the code, the axial requirements are, you know, you get the point. So the code is organized not really in a step process of how you could go through and design a member. As an engineer, without design guides or without somebody going through before you go through with a novel material like the GFRP, you would kind of have to go through the code and go chapter by chapter and get out all those requirements of how you design those members. So part of our goal of creating design guides as part of this project, as part of using GFRP, was to lay out these step-by-step processes. So other engineers that come after us and want to use this material in their building designs can kind of pick up these design guides and say, okay, here's the checks, here's the steps, here's how to implement those steps, and here's the different calculations and the different sections in the code that we have to go to if we have any questions, you know, if something changes in the particular situation of our design of our wall or our slab. And so if we look at, you know, all the different types of members that we have, we came up with these different lists for the design of each of those types of members. And, you know, we're going to go through examples of all the different types of members here. For instance, we're talking about walls. You know, we would go through and define the properties, look at all the ultimate loads, you know, define the FRP reinforcement, check the service bond, minimum bar spacing, you know, and some of these checks aren't part of steel, necessarily designing steel, but they are part of designing in GFRP. Check the creep rupture. That's particularly one of those. Deflection, of course, you know, we're always checking shear capacity, axial capacity, temperature, and shrinkage. And so, you know, through these basic steps, you know, we can come up and design all of the different types of walls that go into the project. So this is a wall schedule that comes kind of right out of the construction documents. If we look at the different walls, we have retaining walls, which are, you know, basically around some of the perimeter in the front, around some of the stuff in the back over here. We also have concrete walls that are retaining walls as well. Those are kind of the ones that are holding up and retaining the soil and the pool that's on the pool deck and back. And then we have CMU walls, which are reserved for the spaces that do not have insulation. So the TMS 402 code within it has both the design of concrete masonry units, which is like your typical block, which we all are pretty familiar with. The other material that we might not be so familiar with is aerated concrete block. Actually, I should say it correctly, autoclaved aerated concrete block. And part of this kind of well-rounded approach, and where your structural engineering is going to run into the engineering of other disciplines, is this aerated block has an insulation value. So usually when you design an enclosure of a building, you need the structure, right? You need the insulation, which isolates the thermal properties from the inside and the outside. You need a vapor barrier and other things that go into that assembly, that wall assembly. Well, what the autoclave aerated block is it actually puts the insulation and the structural material as the same material, right? So that autoclaved aerated concrete has an insulation value. It ranges between an R7 and an R11, depending on the thickness of the wall. And so what we did as part of this project is where we have enclosure or air conditioned space on the inside, we use the autoclave aerated block reinforced with the GFRP for the wind loads for flexure. And so where we have that AAC block, we have some 12-inch in the back, and we have mostly 8-inch around the perimeters. And then, you know, because we didn't want to use drywall, we actually, the interior partition walls are made out of the 4-inch on the inside. And so, you know, the structure and the mechanical or the energy or sustainability, you know, engineering disciplines are really kind of merging at that enclosure of the building, spurred upon by, you know, the glass fiber reinforcement that goes inside. And so the next elements, the foundations that we're looking at. So we took a little bit different approach on the foundations. We were worried a little bit about differential settlement. They have exposed polished concrete floors. So if there's going to be cracking and things on the floor due to differential settlement, let's just say if we use an isolated footing for one column and we use another isolated footing for another column, and those two isolated footings settle differently in the soil, you're going to end up with a crack in the slab up above or in the beam up above. And so we took an approach of doing more of a mat foundation or a continuous foundation. And really, you know, it ends up working more like a beam. And so, you know, spanning over the soil. And so that's why you don't see necessarily isolated foundations. We do have some on the other side, you know, for some isolated columns in the entry and stuff, and one here to support the stair. But for the most part, you know, we wanted to tie all the foundations together so we could limit that kind of differential settlement. It worked out very nicely with the, you know, putting GFRP within there because really, you know, you're designing that foundation a little bit like a beam or like a grade beam. But, you know, similar processes to design them, define the concrete properties, you know, get the ultimate forces, check the bearing pressure, you know, that's underneath those. Design for the one-way and the two-way shear, longitudinal and transverse reinforcement, check the service bond, check minimum bar spacing. That is kind of a critical check and governed a lot of the bar spacing for the GFRP reinforcement. And the development length, you know, any of you that are doing research in GFRP know that the development lengths of the bars are quite different than what they are for steel construction. And so similar, you know, here's the foundation schedule off of the plans. You can see the different ones. We had some retaining footings for the walls in the back, you know, combined mat footing, stair footings, you know, wall footings, and then some, you know, basic things like thickened edges where you have stairs coming down and stuff like that, and around around the perimeter. For the columns, I'm including both the vertical columns and the diagrid structure. The diagrid structure that's in front, you know, when we design, we include some, I guess we call miscellaneous moments on those, just because to make sure that we have any moment capacity for wind forces. You know, you can kind of see the steps there as well on the side. We developed in our spreadsheets, you know, P&M diagrams for these. You know, you can see what they are with the safety factor and what they are without the safety factor. And then we kind of got our shots of where, you know, the different columns end up. You can see, you know, we still have plenty of capacity in the structure over and beyond what the demand is generated within the structure. And so, yeah, that's the columns. The beams, we had both GFRP beams and CFRP beams in the structure. The GFRP beams, you can see, you know, all the members here are highlighted in the BIM model as I'm showing here. but basically around around the perimeters of the slabs, along the edges connecting the columns together. We had some spans in the middle supporting that core, right, that gave us some pretty decent size members. With the GFRP beams, of course, we're designing those to be limited by the concrete strain, right? So under reinforced or over reinforced instead of under reinforced concrete beams. And so what does that mean? That just means that the concrete will fail before the GFRP fails. And really, we do that because of the type of nature of the material, right? The GFRP, unlike steel, it does not have the ductility. It's linear elastic, right, up until the point of failure. And so we want to make sure to stay away from that point of failure of the GFRP. And so we limit the design, and we did that with all the beams. It is allowed in the code to design based on the limit of the GFRP. There's a different safety factor that is implemented in when you go to the GFRP because of its brittle type of failure, its brittle rupture. And so as this being one of the first complete structures designed out of GFRP, we liked having the added safety factor of designing with the concrete failure and keeping the excess capacity in the GFRP on the tensile side and not bumping up against that. And you can see, of course, the steps for designing those beams. One interesting thing was because of the lower modulus of elasticity of the GFRP, and because originally this structure was designed out of steel reinforcement, hence the configuration of the geometry of the overall building, we had some longer spans in the rear of the structure where we had public spaces like the living room, dining room area. Kind of the contemporary design standards is to have that as one big open space with your kitchen in it, dining room, area where everybody kind of hangs out by the TV, and open to the back where the pool is. And so we needed some big spans back there. And so we ran into some deflection issues using the GFRP. And based on that, we implemented using CFRP in these beams, in these longer span beams. And I thought that, this was a great innovation to see how we can be creative as engineers when we run up to, limits of a certain material in the deflection, in the deflection of the beams. And then, we can say, hey, well, what other kind of non-corrosive materials can we use, can we implement in here in order to take care of those individual situations where we might have longer span members that don't meet those requirements. And then we move on to the design of the concrete slabs. Zahid worked on this with myself and Jan and Dr. Nani, of course. The deflections, because the slabs are very, we try to keep them as narrow in depth as we possibly can. The deflections become an issue. The paper that Zahid has coming out, I think it's already accepted for publication, is on the depth of those slabs and creating some design guides along the lines of how deep those slabs are going to be using span to depth ratios like are laid out in the ACI code for steel, just making it easier for practicing engineers to implement that. And so we ended up with a range of slab thicknesses from 4 to 8 inches in depth. And you can see here, we did a comparison because we designed the structure out of steel at the 50% and we designed it out of concrete. And so we did a comparison of what those depths are. So the only difference that we had was in the slabs that were in the rear of the structure. That's kind of these ones back here because the beams are closer together. And we ended up actually, they will work at 4 inches with the GFRP also, but the only reason why we switched them to 6 inches was because we were dropping showers and some other things into that slab, taking up 2 inches of the top. So we decided just to make them 6 inches all the way throughout those. So the decision to switch the slab from a 4-inch slab to a 6-inch slab wasn't governed by the structural requirements. It was governed by a different requirement, an architectural requirement, which required, flush floors everywhere, like where you go into the shower and stuff like that. So what did we get out of this for sharing with the engineering community? We created these design guides. They're available. If you guys would like copies of them, I'm happy to share them with you. We've been spreading these around. We've done some presentations to practicing engineers, showed their availability. Several of them from that presentation at the Florida Engineering Society emailed me. I shared them with them. And so we have these design guides. I'm gonna open up the calculations now and show you guys, but I gotta stop sharing my screen or stop doing the PowerPoint presentation to do that. And then once I kind of go through those, or as I'm going through those, we can answer any questions that you guys might have on the project or on the GFRP engineering. Can everybody see? Can you guys see my screen with the calculations?
Yep.
So, Pranoy, can I initiate the question as we collect questions through the chat?
Yeah, I'll stop the recording as well.
So